In this video, we're going to summarize graphing techniques. There are several parts involved in this process. We summarize it as 4 parts. So mostly we've done all those things in this whole process, except the first part, except those things in the first part, and that's basically algebra. So with the intercepts, with the asymptotes, we'll be able to more precisely sketch graph of function. In particular, when we try to graph a fraction, rational function, the asymptotes play pretty important role, and we'll explain, how we make use of asymptotes to better sketch graph. Intercepts show us where the graph will cross x-axis or y-axis. So those are all like useful information. And in the part 2, part 3, that's what we've been doing. Basically, we try to figure out where the function increases, where the function decreases, whether we have any maximum or minimum value based on first derivative. And we try to determine concaving structures, inflection points based on second derivative. Without that, be able to better sketch graph. All right, so let's see. Now intercepts, it's algebra, and we're going to see how to do it. In our example, asymptote, I want to point out. Although in algebra we learn how to determine asymptote, horizontal, vertical, in calculus there's a different way to do it. In my opinion, better way. So let's first discuss asymptote. And there are horizontal asymptote, vertical asymptote. Let's see how we do some of the things differently, more easily maybe, in calculus. Well, vertical asymptote is the same. So given a rational function, we basically set the denominator to 0. So we set x squared minus 92 equal to 0 and solve. Pretty simple equation. We find x equal to 3, x equal to -3. And that's there are 2 locations where we're going to have vertical asymptote. Okay, that's how we determine vertical asymptote. Set denominator to 0 and solve. X equal to 3 is not just a value x equal to 3, rather it's a vertical line, x equal to 3. So in the coordinate system, it'd be this line through 3. Of course, there's another one, x equal to -3. Okay, the vertical lines, the graph, when we sketch graph, we'll make sure the graph is going to approach those 2 lines. That's what asymptote shows. Horizontal asymptote, it's different. In calculus, actually, in my opinion, it's a better approach. We basically find the limit of the function. When x approaches infinity, so it's the function here. Just find the limit when x approaches infinity. Okay, we can apply L'Hopital rule. We can when x approaches infinity, we even drop lower order term. Just different way to do it. It's probably easier to just drop lower order term. Drop the 9, drop the 4, then x square cancel out. We have the limit simply as -1. So y equal to the limit would be the horizontal asymptote. So again, how to find the vertical asymptote? Set the denominator to 0 and solve. How to find the horizontal asymptote? Find the limit of the function. Here's the function. Find the limit of the function. Then y equal to the limit is the horizontal asymptote. Okay, so find them later on. After we also determine the increasing, decreasing concaving structure, so on, we can be able to better sketch graph. Okay. Let's see this example. Okay, say we want to sketch graph of y equal to 2x squared over x squared minus 1. Okay, so in this part, it's all algebra. How do we find the x-intercept? We set the top to 0. Set 2x squared to 0 and solve, find the 0. That's x-intercept. How do we find y-intercept? We set x equal to 0 in the function. So y will equal to 2 times 0 squared minus 1. Here, replace x by 0. And we have y-intercept as -2. And sometimes you cannot plug in. If you cannot plug in, then you will not have whatever you're looking for. All right, so this is x-intercept and y-intercept. Vertical asymptote, let's see again this function, vertical asymptote. Remember, we'll set the denominator to 0. Now we find x equal to 1, x equal to -1. Okay, we find the 2 vertical asymptote. And here it's a circle, the y-intercept too. How about the horizontal asymptote? Horizontal asymptote, again, we can do find the limit of a function as x approaches infinity. So drop the -1 from the bottom. X squared cancel out. We find the limit to be 2. Then our y equal to 2 is the horizontal asymptote. All right. So this is the part 1, where we try to determine any x-intercept, y-intercept, any vertical asymptote, any horizontal asymptote. By the way, if the function is a polynomial function, not a fraction, then you don't have to worry about the vertical asymptote, horizontal asymptote, because they don't have any. Now let's move on to part 2. In part 2, we try to determine increasing, decreasing, maximum, minimum based on first derivative. So I already find the first derivative function. This is the function. So if we try to find the derivative, well, actually, I think it's a square. right, so with the derivative already simplified like this, we're going to find the critical points. Critical point, since it's a fraction, we're going to set the top to 0 and the bottom to 0. So we find actually 3 of them, 3 critical points. X equals 0, top will be 0. With the x equal to plus or minus 1, the bottom will be 0, derivative not defined, also critical points. Then we create our sign chart. So we have -1, 0, 1. Now we've done this, kind of work. So just make sure this is a sign for y prime. Then you check sign of derivative in each subinterval. Now, this case, denominator is square, so denominator is always positive, right? So don't have to worry about that. Just test out numerator. So pick up, for example, from this section, pick up a -100. -100 plug in, it's positive. -4 times -100 is positive. Like I said, bottom is already positive. It's always square. It's a square, always positive. So just check the top. Top is positive. Therefore, we have positive. Derivative will be always positive. Between -1 and 0, we pick up, for example, -0.5. -0.5 plug in again is positive. Okay, and then just continue be negative or be negative. What does this mean in terms of increasing, decreasing, increasing, increasing, decreasing, decreasing? All right, and with the sign chart here, we can tell there's a maximum value. At this location, there's a maximum. The value is, of course, the function value. Where's our function? Let's recall. Here. So it says at x equal to 0, this critical point, there's a function value. Function value is 2 over -1 because your x is 0. You're going to plug in. Oh, wait. It's actually 0 here. So we're going to plug in 0 for x. This is a 0. So the bottom is a -1. The top is 0. So the function value is 0. Okay, so maximum value is the function you evaluate at 0, which is 0. Okay, it's fine. And that's going to be a maximum. All right, so we know where the function increases, where the function decreases, based on first derivative, and also we detect the maximum value. Now, let's try to determine concaving structure based on second derivative. For this, we need to find inflection point, possible inflection point first. Set the top to 0, set the bottom to 0. The top is never 0, 2x squared plus 4. If you set to 0, no solution. So we don't get anything from top. And if we set the bottom to 0, which is x squared minus 1 equal to 0, we get a plus and a minus 1. All right. Now we create a sign chart for second derivative. Okay, this time it's coincidence. We don't have to worry about the numerator. 12x squared plus 4 is always positive. So all we have to worry about is the sign of the denominator, okay? So check out the interval from negative infinity to negative 1. Pick up negative 10. Negative 10 plug in for x. So that's like basically 100 minus 1, it's positive. Between negative 1 and 1, we choose 0 as a test point. So 0 plug in for x. Again, just the denominator. It's negative 1 to the third power is negative. So the denominator is negative, but top is positive, therefore whole thing is negative. From 1 to positive infinity, finally, we can pick up 5 as a test point. 5 for x, plug in here. This is positive, so it's positive. What does it say about the concavity structure? Going up, down, up. All right, so normally we see change of a concavity structure crossing negative 1. We would claim that at negative 1, there's an inflection point on the graph, but not this case. The reason is negative 1 is not even in the domain. Look at our function here. This is our function. Negative 1 is not in the domain, therefore, even though there's change of concavity structure, there's no critical point. There's no point at all on the graph. Okay? So we don't expect anything here. So nothing. The same at 1. At 1, even though there's a change of concavity structure from down to up, since 1 is not in the domain, we don't expect inflection point at 1. So no inflection point. All right. And then we can try to graph the function, okay? So let's first set up a coordinate system. Mark important locations, points. All right, we find negative 1 critical point, 0 critical point, positive 1 critical point, right? 3, let's be sure. Critical point, negative 1, 0, 1, okay? And increasing, decreasing, and so on. Or there's a maximum, right? There's a maximum value of 0, 2. So let's indicate that. So at this location, we know there's a maximum, therefore the graph must look like this locally. Okay, so mark important points. More. Okay, so there's an x-intercept at 0, y-intercept. I think my y-intercept is wrong. Okay, sorry about that. The y-intercept is actually 0. I thought this was minus. It's multiplication. So it's actually 0. Okay, and there's 1, negative 1 as vertical asymptote, y equal to 2 as horizontal asymptote. All right, so let's mark intercept first. So there's an x equal to 0 intercept. Y-intercept happens to be here, so the graph is going to cross basically the origin. All right, and we also find 2 asymptotes, vertical asymptote. This is a vertical asymptote. This is also vertical asymptote. There's a horizontal asymptote. Let's see. Horizontal asymptote is y equal to 2. So I'm going to indicate that. Let's draw the line down here so we can see more of the picture up. So say this is y equal to 2. Okay, so now let's try to sketch a graph by utilizing the results we find. So let's first start with the decreasing result. Okay, basically we can see here from negative infinity to 0, the graph will all increase. Let's see how we place graph that's all increasing from negative infinity to 0. Keep in mind too, the graph is supposed to approach the horizontal asymptote, the blue line, and the vertical asymptote in green. So we can only come up with this. Increasing, by the way, concaving up to, let's see, that's going to fit into our, expectation. Supposed to concaving up, approaching vertical asymptote, approaching horizontal asymptote, increasing. Now, from -1 to 0, okay, what do we know about the graph? We know it's going to increase. Okay, let's again refresh memory. From -1 to 0, it's going to increase. -1 to 0, it's going to concave down, so it's going to increase. It's going to bend down, and it's going to approach vertical asymptote, right? On the left end, it's going to go through the origin. So this is what we can come up with. It can only be this: going up, bending down, approaching the vertical asymptote, x equal to -1, crossing the origin there. Okay. Now between 0 and 1, let's see the increasing, decreasing first. Between 0 and 1, the graph is supposed to decrease. The graph is supposed to bending down. Therefore, it must be like this. Approaching, by the way, approaching the vertical asymptote too. Okay, and then finally, from 1 to infinity, let's see, it's going to decrease. It's going to decrease. It's going to bend up. It will have to approach the vertical asymptote and the horizontal asymptote. Therefore, it can only be like this. All right, and you can see here at the origin there's a maximum value. Okay. All right, let's stop here.